Suppose we have a circuit like this where we have three impedances, mixed impedances, two that are in parallel and the other one that is in series with the two, and we are asked to calculate the current, the voltage drops, the power consumed by the circuit, and we start by calculating the equivalent impedance. We can say that the equivalent impedance is Z1 in parallel with Z2 plus Z3. Let's write Z1 in polar form, that's what we need later. It's 14 plus J12. In polar form, this is 14 squared plus 12 squared, and argument is arctangent of 12 over 14. That will give us Z1 equals 1844. This is the module. The argument is 40.6 degrees. Z2 we can write as 16 minus J18. In polar form, it's 16 squared plus minus 18 squared, and arctangent of minus 18 over 16. This will give us an impedance of 24.08 and argument minus 48.37 degrees in ohms. Now we can calculate Z1 plus Z2, which is equal to 30 minus J6, and in polar form it's 30 degrees squared plus 6 squared, and argument arctangent of minus 6 over 30. That will give us a value of 30.6 and argument minus 11.31 degrees in ohms. Now we can calculate Z1 in parallel with Z2. This is Z1 times Z2 over Z1 plus Z2. So Z1 is 18.44, argument 40.6 over times Z2, which is 24.08, and argument minus 48.37 degrees over 30.6 minus 11.31 degrees. So this times this over this will give us a value of 14.51, and argument 40.6 minus 48.37 plus 11.3 will give us an argument of 3.54 degrees. And in algebraic form, we can write 14.5 about plus J 0.898, and this will give us Z equivalent is this one, 14.5 plus J 0.898 plus Z3, which is 10 minus J8. This will give us equivalent impedance of 24.45 plus minus J 7.1, and the polar form is 25.5, argument minus 16.17 degrees. This is the equivalent impedance. Now we can calculate the currents. The main current is equal to V over the equivalent impedance, and it's 230 divided by 25.5 minus 16.17, and this will give us current of 9.02 plus 16.17. Knowing this current, we can calculate V1, which is equal to V2. V1 is equal to Z12 times I, and this is equal to Z12, which is here, it's 14.51, 3.54 times 9.02 and 16.17 degrees, and this, the voltage will be equal to 130.94, and argument will be 19.7 degrees. This is in volts. We can calculate V3's voltage drop here. It's Z3 times I, and this is Z3. Where is Z3? Do I have it? Z3, I didn't put it in polar form, but it's 12.8. Argument minus 38.66 times 9.02 are 16.17, and this voltage is 115.45 in volts, and argument will be minus 22.5. About. Okay, from now we can calculate I2 and I1. I2 is equal to V1 over Z2, or E1, I1 first. I1 is V1 over Z1. V1, it's 130.94, 19.7 degrees over Z1. Z1, I forgot about it. Z1 is about 18.44 and 40.6 degrees. I1 will be equal to 7.1 and minus 20.9 degrees. Now we can calculate I2 is V1 over Z2. It's 130.94, 19.7 over Z2. Z2 which is equal Z2, which is equal to, here we have it, 24.08 minus 48.37 degrees. Here now we can say that I2 is equal to 5.44, the argument this plus this 68.1 in amps. So we calculated all the currents. I can draw the vector diagram of all of these and instantaneous values. This is the main voltage V, V3, V1, I, main current, I1, I2, and these are the instantaneous values V, I1, I2, I, the main current, V1, and V3. Now we can calculate the powers taken by every element here. This is S1 consumed by Z1, Z2, Z3, and the main, the power delivered by the source. So here it's V1 times the conjugate of phi1 will give us value of this. P1 is equal to 705 point. Here it's point, it's not comma, plus J, 604, this is Q1. Here P2 is equal to 474. This is V1 times the conjugate of phi2. Here it's V3 times the conjugate of main current. Conjugate of this main current will give us a P3, a Q3, and the main power delivered by the source will be V times the conjugate of the current. That will give us main P, that is equal to 1992, and Q is minus 578, and the main power should be equal to the sum of the three, and you can verify the results. And thank you for your attention.